Now it is my great pleasure to be able to introduce to you our next speaker, Dr. James E. K. Hildreth. Dr. Hildreth is the Dean of the College of Biological Science. He's a professor of cellular and molecular medicine, as well as a professor of internal medicine at the University of California, Davis campus. Dr. Hildreth was born and raised in Camden, Arkansas. I'm not going to say the year, it's in the bio. And began his undergrad studies at Harvard University. He was selected the first African-American Rhodes Scholar from Arkansas. He graduated from Harvard magna cum laude in the field of chemistry. In fall of 1979, Dr. Hildreth enrolled at Oxford University in England, graduating with a PhD in immunology in 1982. At Oxford, he studied the biology of cytotopics, T cells with Professor Andrew McMichael, and became an expert in monoclonal antibody technology and cell adhesion molecules. He returned to the United States to attend Johns Hopkins University School of Medicine in Baltimore, taking a one-year leave of absence from medical school for a postdoctorate fellowship in pharmacology from 1983 to 1984. In 1987, he obtained his MD from Johns Hopkins and joined the Hopkins faculty as assistant professor. In 2002, Dr. Hildreth became the first African-American in a 125-year history of Johns Hopkins School of Medicine to earn full partnership in tenure in the basic sciences. Dr. Hildreth served Johns Hopkins for several years as the first Associate Dean for Graduate Student Affairs. In July 2005, Dr. Hildreth became Director of the NIH-funded Center for AIDS Health Disparities Research at Meharry Medical College. Dr. Hildreth has received numerous awards over his career for mentoring, leadership, and his efforts related to diversity. In October 2008, he was honored for his contributions to medical science by election to the Institute of Medicine, part of the National Academy of Sciences, the most prestigious biomedical and health policy advisory group in the United States. Dr. Hildreth has trained several junior scientists over his career, including 19 PhD students. In August of 2011, Dr. Hildreth became Dean of the College of Biological Sciences at the University of California, Davis. What's natural law is definitely California gained. He was also appointed as a tenured professor to the Department of Cellular and Molecular Biology, as well as a professor in the Department of Internal Medicine at University of California, Davis School of Medicine. I'm not going to read any further of Dr. Hildreth, but to make a long story short, before you leave here today, definitely introduce yourself and shake his hands, because we are in the presence of one of the most talented researchers of our time. So, in a couple of years, maybe in a couple of months, you can say that you were in the room and in the midst with Dr. Hildreth. So, without further ado, Dr. James Hildreth.
Good morning. Good morning. First, I'd just like to say I'm so grateful to Ed that he thought it not robbery to ask me to come and speak with you this morning about my work and about my life as an HIV researcher. When I moved to Nashville, Ed is one of the first people I was introduced to, and needless to say, someone I really want to know, because Ed was a minister who was one of the very first to embrace the AIDS fight and bring it right into his church, which is a very powerful thing. And I think over the last 2 decades, he's become a national treasure for all his hard work and all the influence he's had. So I'm just really grateful to be still, that he honors me enough to think enough of me to come and be with you today. The other thing I want to say is I'm going to talk about a lot of things, and in putting my talk together, I was reminded of my growing up in Arkansas. I lost my dad when I was 11 years old. And I was in a house with 4 sisters and a mother. My 2 brothers were 10 years older than me plus, so there was a lot of estrogen in the house. And my mom got me into the Boy Scouts, and I eventually became an Eagle Scout. But my next door neighbor also took me under his wing, Mr. Leander Watson. We call him Mr. Leander. And he took me fishing, did lots of things with me. He also took me hunting. And we'd hunt deer, but his favorite thing to do was to hunt squirrels. You know that famous brand of tuna called chicken of the seas? He calls squirrels chicken of the trees. Anyway, we would go hunting for these things, and I think I was about 12 or 13. He would always get a kill, right? But I never seemed to be able to. Then one day, I'm sitting on my back porch, my mom's back porch, just thinking about that, because I've been a scientist since I was 7 years old. I need answers, right? I need to know, why can't I kill a squirrel? So as I thought about it, I went through all the parameters, you know, the projectile ratios and all that stuff that people think about. Then it occurred to me, I'm using a Remington single-shot 22 caliber rifle. Okay. Mr. Leander is using a 12-gauge shotgun. Now, if you aim the shotgun anywhere in the tree, whatever's in the tree is coming down. Squirrels, birds, whatever, cats, you know. So anyway, when I give my talks to my colleagues in research and science, I'm usually giving a 22 caliber talk. That's right on some specific topic, but today's talk is going to be more of a 12-gauge talk. I'm trying to cover a lot of things, and I hope that 1 or 2 of them you might find edifying or at least interesting as I walk you through this talk today. But I also wanted to just pay homage to one of my lost colleagues and friends who about this time last year we were sending on to glory. And Reverend Sanders already mentioned Jackie Hampton, whose work, as far as I'm concerned, is legendary. She really taught me about how important my work could be if I got it beyond the bench, out into the community. She taught me a lot of things about that, so I'm very grateful to her. So I'm going to cover a lot of things. I'm going to go through really quickly, but please feel free to stop me and ask questions if you need to. Some of the things that I'm going to say you've already heard, I'm sure. Some of the things you may already know, but repeating can be important just for emphasis and to keep the conversation going. So I'm going to talk about the global epidemiology of HIV, talk a little bit about the epidemiology throughout the United States, talk about my own research, which I'm very excited about, and then add one that means to share with you some recent developments that give us hope that the end might be at hand. Okay. So, as you know, AIDS is a chronic debilitating disease caused by the destruction of the immune system. Every day, all of us, no matter who we are, our hygiene, where we live, what our profession is, we get exposed to billions and billions of microbes that have the potential to make us sick. And I became an immunologist because I happen to think the immune system is one of the most important systems in our body, if not the most important, because it's what keeps us protected from all these microbes. Every time you take a breath, you're breathing in microbes you cannot see, but the fact that your immune system functions keeps you protected. And so AIDS is the devastating disease it is because it causes a failure of the immune system. And we all know that what those symptoms are. I'm going to talk about that a little bit more in a minute. But one of the things to know is that HIV infection can be silent. Many people who become infected have no awareness whatsoever that they become infected. There are no symptoms that they are aware of, where there are others, when they get infected, they have a flu-like syndrome for a few days. This slide shows you the natural history of HIV infection, just as a reminder. Thankfully, most of the time now, we don't see this natural history playing out because eventually people get into care. Just as a way of a reminder, there is infection that occurs. The red line are the viruses. The blue line are the CD4 positive T cells. So after infection, there's a transient rise in the viral load that subsides after 10 to 12 weeks. There's also a coincidental dip in the CD4 count. They both stabilize through an asymptomatic phase. And we have what's called the virus set point, shown at the bottom there. And that can be high in some individuals, can be low in other individuals. And in some individuals that we call elite controllers, you can barely find any virus in their plasma because they're controlling the virus very well. But then at some point, it can be months to years later. In fact, when I was at Johns Hopkins, we saw the individual who'd been infected for 16 years. And you could not tell that this man had anything wrong with him whatsoever. But his CD4 count was, I think, about 300. His viral load was about 10,000 to 20,000. He looked perfectly healthy. He'd been infected for almost 20 years. But anyway, at some point, the virus starts to replicate the pace again. The CD4 cells start to drop, as you know. And when the CD4 count drops to a certain level, they begin to get opportunistic infections, and then they're defining as having AIDS. So this is just a review of the natural history of the infection. And one of the concerns we have, of course, is that many people, especially African Americans, come to the attention of care providers very late in the game, when you're in that third box, and when you're in that third box, the outcomes are not nearly as good as they are if you're in those first two boxes.
Doc, quick question. On the guy that came to you in Baltimore and said he had the disease for 16 years, was it because the history was documented he had had that?
Yes.
Okay. It wasn't that you could project that you had that?
No, he was kind of like magic. He was someone who came to the attention of the caregivers very early in his infection. This slide just reiterates what I said before. As an immunologist, I have an old slide here where we still call the CD4 cells T4 cells. When I was a graduate student in the late 70s, early 80s, we call them T4 cells. But my point is that if HIV had chosen any other cell type in the body to be its target, it wouldn't be the devastating disease. It might be some other devastating disease, but it's this devastating disease because it's wiping out the conductor of this orchestra. CD4 T cells conduct the activities of B cells, macrophages, T8 cells. And when you knock them out, it's like you're knocking out the general of an army. There's chaos and disorder, and that is really why the virus is so devastating. I think it's fair to say that HIV itself probably has never caused the demise of anyone. It opens the door for other things. And there's no system in the body, really, that cannot be impacted by HIV because there's an infectious agent that can infect all the tissues in the body, the brain, the skin, the digestive tract, the liver. And when HIV suppresses the immune system, as shown on the slide, on the left-hand side are symptoms, the right-hand side are the infectious agents that cause the symptoms. You can see that the range of infectious agents from Candida to Cryptococcus, there's a whole range of things that can get into our bodies and make us sick and cause these problems. But it's not HIV itself, it's those other things that it's open the door for. And that's also true for all of the organ systems, including the digestive system. But there are some peculiar pathologies that we don't quite understand. For example, when African Americans get infected, we often get what's called HIV-associated nephropathy that you don't really see, for the most part, in other racial groups. And so one of the things that we were doing when I was at Meharry was trying to understand what is the basis, is it biological or otherwise, for these pathologies that we don't understand. But just to make you aware that there are some diseases that occur in some racial groups that you don't see in others. Yes?
What's nephropathy?
Nephropathy is an inflammatory disease of the kidney. So, just a little bit of history, because again, when I'm putting this talk together, I got a little excited, maybe I put too many slides up, but anyway, we're 31 years into knowing about HIV. The first cases were, of course, described on the two coasts, the West Coast and East Coast, in 1981. And unfortunately, it was given the name gay-related immunodeficiency disease, or GRID. You might all recall back then when our president, then Ronald Reagan, a couple years later, unfortunately put a stamp on this. His imprimatur of making this a gay-related disease really set back the effort, in my opinion, in very significant ways. But you're going to see in just a moment, this has never been the disease only of gay white men. Then, that same year later, in really the most prestigious medical journal, the New England Journal of Medicine, there were 4 reports in this one issue in the New England Journal of Medicine describing an outbreak of infections that really should not occur in young, healthy individuals. And at this point, we all knew that we had a serious problem. In a rapid fashion, just 2 years later, this very colorful scientist from France, Luc Montagnier, actually isolated the virus. And with all due respect to my friend and colleague, Bob Gallo, this is the man who discovered the virus. Anyway, in rapid fashion, just 2 years after those reports, we'd identified, or a team had identified the virus. And this makes the point that from the very beginning, the research effort on HIV has been very intensive. In fact, there seldom have been a mobilization, at least in my field, immunology and cell biology, like the one that occurred after HIV was discovered. Then also, quite amazingly, just 4 years after that, the first drug hit the market to treat HIV, AZT. And this is remarkable because ordinarily it might take as long as a decade, sometimes 2 decades, to go from a small molecule to a approved drug. And in this case, now mind you, this drug was already being studied as a cancer treatment, I believe, but to have it approved for treatment just 4 years after the virus was discovered is a pretty amazing point. But it speaks to the intensity of the effort that's been underway from the very beginning to find an answer. I've always been asked this question, so I just made it a routine part of my talk. HIV was not created by mad scientists bent on destroying black folks. Okay? HIV is almost certainly a zoonotic infection, meaning zoonoses are infections that arise and jump from animals into humans. And HIV is almost certainly an example of that. Because this very day, to this day, if you go to the west coast of Africa or other places and trap monkeys, chimpanzees especially, you can isolate from these animals a virus that's 99.9999% identical to HIV. And what probably happens is, it might have been even Europeans for all I know, individuals who trap these animals, who are bitten or scratched or otherwise resulting in the virus having access to our system. The other thing is to keep in mind is that monkey brains and monkey meat is food for some people. And that might have been another possible reason. But we are convinced, those of us who have been studying the virus for a long time, that HIV is the result of a zoonotic infection. It jumped from monkeys into humans.
Are there other examples of
zoonoses?
Yes.
Yes. The most famous one, of course, is avian flu. You can only get avian flu by having interactions with birds. Now, the scary part would be if the virus mutated so that it could go from one person to the other. But for avian flu, at least, some strains of them, you can only get infected by having interactions with an infected bird. There are other examples as well, but that's one that most people are familiar with. So the other thing is that HIV is not a new problem. There's evidence, lots of it, that people have been infected by HIV for decades. This just shows you 3 examples. Plasma taken from an adult male in 1959 from the Republic of Congo. PCR test showed that this man had HIV infection. There was an American teenager who died in St. Louis in 1969, same thing. A test of her tissue showed that she was HIV positive. Then there was a sample found from a Norwegian sailor in 1976, also HIV positive. One of my colleagues who does what I call molecular anthropology, where she uses DNA sequencing to determine the origin and age of certain infectious agents, her beautiful data shows that HIV has been infecting humans probably since the 1920s and 1930s. And there is data that has not been validated, which I'm aware of, which indicates that someone who died in 1894 was probably HIV positive. So this is not a new problem for humans. And obviously if there are viruses that have, if we've been infected since the 1920s, that should refute any suggestion that the virus was created by mad scientists. Because molecular biology itself did not exist just a few decades ago.
Dr. Hildreth,
yes.
when you say this data, are we talking about tissues taken from cadavers in the 20s?
Yes.
Proven to have.
Well, in this case, she used what I call it molecular anthropology, where you can take DNA sequences, and by comparing the DNA sequences from different viruses, you can estimate how long it took for the new strains to evolve by mutation. But it's pretty powerful. And knowing that there are actually samples of individuals who died back then and who were positive, the data sort of confirm each other. But the other thing you should know is that 10% of the human genome represents past infectious events in which retroviruses like HIV have left their genetic material in our genomes. 10% of our genome thereabouts. So retroviruses have been infecting humans for a very long time. So the estimates are that right now somewhere between 30 and 35 million people around the world are HIV positive. But I want to draw your attention to the fact that the epicenter of the problem is Africa. 2/3 of the people infected by HIV live on this continent, and about half of those, at least half of those individuals live in the southern half of Africa. But the point is that this is a true pandemic. All parts of the world where there are large population centers, they have an HIV problem. And that's the definition of a pandemic. It's global. And this problem certainly is. The global prevalence of HIV for adolescents and adults is 0.8%, just south of 1%. But again, if you look at Africa, shown there in the middle, the prevalence is just under 5%. So the prevalence there is 5 times the global average. And again, it reflects the fact that Africa is such a hotspot for this. And there are currently about 1.8 million new infections per year, deaths per year, and 2.7 million deaths. 1.8 million deaths per year and 2.7 million new infections per year. So the problem is not getting any better really in many ways. So that kind of gives you a picture of the global situation. I just wanted to make the point that in Africa, this has truly been a devastating problem. And this slide here makes it very well. This shows you life expectancy in 5 countries located in the southern part of the African continent. Botswana, South Africa, Swaziland, Zambia, and Zimbabwe. You can see that between 1970 and 1990, they were doing an excellent job of increasing life expectancy to many kinds of interventions, health-wise and public health-wise. But look at what happens when HIV becomes a significant problem in the mid-90s. And most of this can be attributed to HIV. There's lots of studies to confirm this. You can see that the life expectancy went from 55 or so down into the mid-30s. Wow. Okay, so the life expectancy took almost a 50% drop due to this one infectious cause, which is really devastating. So I didn't lose quite enough weight, huh?
Thank you.
Can you see?
There we go.
You want to stand up there and I'll
No, I mean, it's okay. It's okay. This is very important, though.
Right.
This is one of those slides that to me brings home every day why I do what I do. Because this is a devastating thing to see. And I see this one infectious agent, one pathogen, can have such a devastating effect on life expectancy. Given all the work and effort that had gone into getting to where it was, in terms of food, clean water, all those things, look at this. This is really, really, really amazing. So, you've already seen this for the Alameda County, but the national data, this is now data for the United States. These are from the 40 states, I think, that have named reporting, mandatory reporting. You can see that in the mid-90s, as you just saw earlier, there was a dramatic change in the trends. This is when ARTs, antiretroviral drugs, were introduced. You can actually see that now diagnosis of AIDS, people with those opportunistic infections, and deaths from AIDS plateaued. And there's been a gradual decrease over the last few years, but that was a pretty significant development in our effort to combat AIDS, where we've got plateauing of these two curves. What you don't see is that the prevalence has continued to increase because, as you heard earlier, from Adrian. It's Adrian, right?
Yes.
Okay. That the number of new infections continues to be a problem. And depending on which model you use or whose data you use, somewhere between 40 and 60,000 people are newly infected each year. Now, you've already heard that globally this has become a problem primarily of people of color, but that's also true here in the United States. These are data from the CDC going back to 1985 up until 2010. I just want to make a couple of points, one of which I made already. Even back in 1985, you can see that a fourth of the HIV infections or AIDS cases occurred in black folks, African Americans. Not only that, there was a significant number of Hispanics infected. Okay? And you know, non-Hispanic whites accounted for 59 to 60%, but the other 40% were other people. So this never has been a problem of gay white men. It's always been a problem that affected the whole population. The other thing is that you'll notice that for non-Hispanic whites, this has become a problem of diminishing importance. It's still very important because it's impacting everybody. But the curve there for African Americans, you can see, is not one that we should be comfortable with. Now the trend shows us sort of plateauing, but that could be deceptive for a lot of reasons. But anyway, I just want to make the point that clearly this is a problem that we really need to be attentive to because it's really impacting people who look like us.
Hildreth, I have a question.
Yes.
If this is affecting people of color globally, do we understand why?
Well, a lot of it has to do with resources, access to resources, education. Some of it's just focus, and some of it's cultural practices and attitudes towards sex and talking about sex. Now, we got experts in the room who can talk about that, so I like to stay in my orbit. My orbit is molecules and cells, so I'm not going to get too far out of that. But there are so many things that impact that, and that's why it's really important that we have people of so many different disciplines, sociologists, behavior scientists, all involved in this. And I'm just trying to do my part by understanding those things we can't speak.
And I appreciate that. Thank you.
This might also be interpreted the fact that black people are actually, if they're getting more diagnosed, that they really are accessing health care when they're getting diagnosed with greater frequency?
Well, thankfully that is the case, that more and more, as we increase our awareness and the messages are getting out thanks to efforts by folks like yourself, that is increasingly the case. But there's also some issues that you'll be dealing with related to stigma, et cetera, that are still significant barriers for us. But again, it's the whole orbit.
Yeah.
Just going back to the previous,
Yes.
like at the start of the epidemic, it stands to figure that for the blacks and Latinos, the figures were actually higher. There was just no access to testing and diagnosis.
And I think that point was made earlier, that this shows us what we think we know, but the number is something like 1 person in 5 or 1 person in 4 globally who's infected does not know, is not aware of their status. The only point I want to make here is that where I come from in the Bible Belt, there's a whole lot of denial going on. Am I still getting on toes? Okay? But you can see the Bible Belt got a whole lot of HIV going on. Okay? And if you live in Georgia or Florida, or Maine, surprisingly. Maine? Anyway. So this problem is occurring in places where some people think that maybe it shouldn't be. You know, rural southern communities are now really being hit hard by HIV. And that just makes a really important point, that this message needs to get out to all parts of our communities, wherever people are.
Maine has a lot to do with social stratification. Population is not high, but First Nation people,
Yes.
as a part of the live in concentrations and isolated, and they have identities.
Right.
And aren't these red states?
Aren't these what?
Red states.
Oh, I'm not.
I know, that's not in your office. I
So this point just confirms what you heard earlier for Alameda, that African Americans account for 13% of the population, shown there on the right, but over half of the diagnosed HIV cases as of 2009 in those 40 states that have name-based reporting. So this shows you how disproportionately impacted we are as a group compared to other population groups in the United States. And if you break this out by gender, I think that's the next slide. This has really driven my own personal work for the last 2 decades. Obviously, African American males account for the preponderance of diagnosed HIV infections, shown there on the left. The purple, I think it's purple, the big tall bar. Okay. If you go there to the right, it's shown for females. And here's where things, I think, are just totally unacceptable. That African American women account for 2/3 of all the new infections by HIV.
Yes.
And in some parts of the country, Washington, D.C., Atlanta, a few other places, the numbers might even be more devastating. Yes, sir.
Will we be afforded copies of your slides, maybe?
Yes. But the point is that this is clearly a problem that disproportionately impacts African Americans and Hispanics. But for women, and this is also true globally, that women have now become, in some places, the fastest growing group of people affected. This is a significant problem. And this is a slide from a couple of years ago, because when I heard this news, I was really, I couldn't really believe it, but I guess it makes sense. In a study commissioned by the Washington, D.C. Department of Health, this is from 2010, they actually found that 3% of African American adults living in Washington, D.C. are HIV positive. Now, mind you, we're sending billions of dollars to countries in Africa that have rates of infection just in the same order of magnitude. So you might think that maybe we need to send cut for our funds to DC. But my point is that these numbers are staggering and make you sit up and get attention. That if in our capital we have a situation like this, we have a serious problem on our hands. Okay, so there are 3 strategies broad strategies for ending this pandemic.
Doctor,
Yes, sir.
on your previous slides,
Uh-huh.
at the very bottom,
Oops.
very bottom is 10% of men between ages of 40 and 50. Does that represent people just living with the disease longer? Or does it represent the possibility of older men that start getting above?
The question was, does that 10% of African American men between 40 and 50 reflective of people with HIV living longer? The answer is yes, because of the drugs. But the second part was whether or not older men are getting infected. Yes. One of the things I say to every group I talk to, whether you're 8 hours old, actually minus 8 hours old, still in the, or 88 years old, you can become infected by HIV.
Yeah.
If you're a normal human being with CD4 positive T cells in your body, it will infect you. It doesn't matter what you look like, how much money you make, where you go to school, what kind of car you drive. Okay. Sorry, I'm getting out of my. Okay, I'm allowed to do that every now and then. And I'll just tell you one story, which is a true story. And I know you've heard stories like this. Because I was told this story about a person it happened to. They go to the nursing home to visit their mother, who was 78 years old, I believe, at the time. And it's told that their mother is HIV positive. Okay? And she got HIV by having intercourse with another man in the nursing home who became HIV positive. When his check came the first of the month, he bought the services of ladies of the night who gave him the virus. He then passed it on to this person's mother. So those little blue pills, or are they purple? I don't know what they are. they've had a significant impact on this problem. You can't make this stuff up.
Right.
My point is that all age groups are being impacted by this because everyone is going to have sex. Okay. I'm sorry, I'm just...
It's true.
Right?
We in the house.
So older people are getting
We in the
infected
house.
because they happen to have CD4 positive T cells, and HIV does not care who you are, what you look like. And this is one of the messages that we need to get out.
We hope she
Yeah, seriously. Okay, so moving right along, let me get back to that. So there are three major strategies for ending the pandemic. The first is therapeutic agents. Thankfully, there are now more than 20 drugs that are quite effective in suppressing HIV replication. You're going to hear in just a moment an exciting new use of these drugs, perhaps, to prevent transmission of the virus. Prophylaxis is the thing that we're most hopeful for. Prevention is the real key to all of this, preventing new infections in the first place. And there are 2, 3 things we can think about. Vaccines, which are very challenging, but we still are hopeful that we can make one. Microbicides, which is one of the things that I work on. And these, you're going to hear what these are in just a moment. Condoms, if you are a man, you don't want to get HIV, you have 2 great options available to you to keep yourself protected. You can keep your willy in your trousers and abstain from sex. You won't get infected. Just don't engage in sex. Abstinence is a great. Or, if you or your partner use a condom appropriately, you can be protected. If you're a female, on the other hand, on the receiving end of 3 to 7 cc's of seminal fluid with billions of HIV particles in it, and the act of having sex itself always, always always causes microscopic, unseeable damage to the frog and mucosa that lines the vagina. And your chance of getting infected. And that's why male to female transmission appears to be somewhat more efficient than the other way around. And that's why empowering women to protect themselves should be a goal that all of us should be trying for. Sorry, I'm getting it. Then behavior. This might be the least expensive but most difficult. Getting people to change their ways. Believe me, being the father of 2 kids, I can tell you that getting someone to change their behavior is a really tough thing. And the older they get, the tougher it gets.
Yes.
So this is still something that we should try for and strive for, but it can be challenging. Let me just say quickly, with all due respect to my colleagues who work on vaccines, billions and billions of dollars have been spent in trying to make an HIV vaccine by some of the smartest people on the planet. And so far, we don't have one that seems to work very well, but I think it's coming. The reason for this is that this virus is very smart. And I hate talking about it like it's, but it is. It's almost as if the virus went to medical school, took an immunology course, and knows all the things it needs to do to evade being eliminated by the immune system. But one of the most significant things is the rate at which it mutates. Vaccines are designed to give the immune system memory of something you've been exposed to, and then the next time you see it, there's this expansive, massive response to it to keep you protected. So vaccines are designed to do that, to get your immune system knowledgeable and ready for the next time you see that thing, that particular thing. But if HIV is mutating, and you don't see the same virus that you got vaccinated against, then by definition the vaccine will not work. And this virus mutates so fast that if you take an HIV patient in January, isolate the virus and sequence it, bring them back in May and do the same thing, you will find that those same sequences might be there, but there are now dozens and dozens of others because the virus has mutated to become what's called a quasi-species. Yes, sir?
So what does that mean for people that are getting infected with mutated strains and the medications maybe not work for them?
Well,
So does that happen?
well, the 2 things are definitely related. One of the reasons why early on in the treatment of persons with HIV, that they had to be religiously adherent to their regimens, is that if they weren't, the virus would mutate and become resistant to the drugs. And in some cases, they became resistant anyway. Because the drugs are like a key that fit into a lock. But if the lock changes shape, the key no longer binds to the lock. And that's what happens when viruses mutate. Proteins change their shape. And in the same way that the immune system is recognizing shapes, drugs are also recognizing shapes. So the high mutation rate of HIV is responsible both for resistance and the difficulty of making the vaccine. Both things are directly related, if that kind of makes sense.
It does. Thank you.
So, and as I've already said, the virus appears to inactivate the very cells that are designed to eliminate it.
Yeah.
So if you have a virus that's killing off the immune cells, then that's going to make it very difficult, in fact, to generate a vaccine. And there's actually evidence, which I don't have the time or technical slides to show you, that the cells that are responsive to HIV might be more susceptible to infection in the first place. So the virus is fiendish, is the bottom line. So the other thing is, microbicides are an alternative to vaccines. Microbicides are gels or creams that are applied topically, that is to the skin. And technically the vagina is an extension of the skin. They're all epithelial cells. They just happen to be located in different places. And the idea is that a physical property of the virus or bacteria will be targeted, and that microbe will be killed. And there are specific types of compounds that can be used. Drugs, detergents, polymers, there are many different things that can be used. But the basic idea is that the woman would apply, or in the case of anal sex, these creams will be applied to the rectum or vagina. Okay. HIV would come into contact with the chemicals in the gel or cream and be inactivated, and the person would be protected. That's the basic idea. And if you target a physical property of the bacteria or the virus, such as a structural component, resistance becomes unlikely. So that's one of the very appealing things about this approach. But this has challenges as well. Okay? First of all, in order to design something to block HIV transmission, we really need to know how transmission occurs in the first place. And being perfectly honest with you, we're not quite there yet. For example, there's still a debate as to whether it's free virus particles or infected cells that cause transmission. Is it a Trojan horse mechanism in which infected cells in the genital secretions are moving from one person to another, or is it the free virus particles? We don't, for example, know which cell types become infected first. Is it dendritic cells or T cells, etc.? So there are some challenges to making a microbicide. Some of these have been overcome. For example, there are places in Africa still where, this may be less and less as the years go by, where dry sex appears to be the preferred sex, where women physically try to dry themselves out before intercourse to enhance the sensation or make their partners happier. But anything you do, whether it's tissue, paper, or leaves, or a towel, indeed, will damage, again, that friable, delicate surface that lines the vagina and make it more likely that there's transmission like this. Other STIs, other sexually transmitted diseases can enhance transmission rates by as much as tenfold. So there are all these things that we have to deal with in trying to design a microbicide that we think about every day. Now, very quickly, in my last few minutes, I'm going to tell you about our research. I'm going to go through this really fast because I want to save time for questions. HIV is a virus. Viruses have life cycles that involve several steps. HIV must first attach to a cell. It does that with two receptors, CD4, which we all know about, and the chemokine receptor. Those individuals that you've heard about, the delta 32 mutants, do not have the chemokine receptor, so they're resistant to infection. That is why some individuals can be exposed up and over again without becoming infected, because they don't have that second receptor.
Dr. Hildreth, is that the case of the prostitutes in Central Africa?
No, the prostitutes in Central Africa is a different story, and maybe some of my colleagues here might have some other information, but as best I can tell, they are not delta 32 mutations. There's something else. interesting going on with them. And needless to say, they've been extensively studied from a whole different range of viewpoints. Their HLA types, their genetic backgrounds, the genetics of their viruses, but does not appear to be this issue. So after the binding infusion, the RNA is injected into the cell, it becomes DNA. The DNA becomes integrated into the host cell DNA. This is really important because this is why HIV infection is an infection for life. The viral DNA becomes part of the cellular DNA, but there are some cells in our body that have half-lives measured in decades. They divide so slowly that that same cell would be physically present in your body for as many as 10, 20, 30 years. Okay? But because they are able to divide, that means that when you become infected with HIV, we have to assume that you're infected for life. So Magic Johnson, who looks perfectly healthy, robust and all that, I'm pretty sure he's still taking medications because the virus is still there. And this is why, because of this step called integration, where the viral DNA becomes part of our DNA. Yes, sir?
That was the question I was going to ask you. So I was in a presentation in a physician, and he explained it similar to what you're saying. He said, so there will never be a cure because it becomes a part of your DNA. Is that correct?
Actually, there is already a cure by, well, yes, I will call it a cure.
Okay.
There is a young man, young compared to me, in Europe who had both HIV and leukemia.
Okay.
They ablated his bone marrow, that means they destroyed his bone marrow, and gave him a bone marrow transplant from a donor who had the Delta 32 mutation. So this new bone marrow has cells that are incapable of being infected by HIV. So they repopulated his immune system with Delta 32 mutated cells. And I believe it's now 3 years, and maybe a little longer. Do you happen to remember how long it's been? Yes. Something like three years now or more, he's tested completely positive for HIV by the most sensitive test available.
So how does that affect his DNA?
Negative, I'm sorry.
So how does that affect his DNA?
Well, the DNA in his stromal cells, the cells that make up his structural components of his body, are still his DNA. But the DNA in his immune cells are now the DNA of the donor. And that DNA lacks the Delta 32. Because HIV infects cells in the immune system, he's essentially now resistant to infection.
What happened to the leukemia?
It was cured. They did this treatment to treat his leukemia, but in doing so, they also cured his HIV. Now, this is very exciting, but you think that there's 30 million people infected. We can't do, this is not a practical solution for costs and for also the fact that you have to find a DNA match or a genetic match for each person. It would cost uncountless billions of dollars to try to do this for everyone who's infected. But technically then, we could actually say, this gentleman has been cured.
Okay. Thank you.
Was there? Okay. I'm sorry, so after we get integration, we get new proteins being made, the virus assembles and released. My research since 1986 has been involved in the first step and the last step. The virus going in and the virus coming out. My research began with a very simple question, and that is biological complexity and biological diversity generally is accorded with the number of genes an organism has. Human beings are wonderfully complex, marvelous machines and individuals because we have somewhere between 25,000 and 30,000 genes that encode all the proteins and systems that make up our bodies. HIV only has 10,000 base pairs and just a handful of genes shown across the top. Now, by comparison, herpes simplex or cytomegalovirus or some of the other large DNA viruses have 10 times to 100 times as much genetic information. Yet, in many ways, the biology of HIV rivals or even surpasses those other viruses. So how can it be that a virus with such modest genetic information has such amazing biological complexity? Our hypothesis was very simple, that HIV is a thief and that it's stealing proteins from the cells, that it's acquiring the proteins from the cells, using those proteins for its own benefit. It does not need to encode those proteins in its DNA. It's simply going to take them from the cells that it infects. And to make a long story short, the work of at least 5 to 6 graduate students, we proved that that's exactly the case. That when you look at an HIV particle, it's not just viral proteins that are there. There are lots and lots of proteins that actually derive from the host cell, and these proteins retain their function. And that is why HIV is able to achieve this biological complexity. Not only that, it's also subverting many pathways, systems in the body. And that's how it's able to achieve this complexity. This slide just summarizes that the virus is doing what we said. It has lots and lots of host proteins. In fact, we have a technique called proteomics, which you can take a complex mixture of proteins and sequence them to determine how many are there. And if you do that on an HIV particle, it turns out that in terms of types of proteins, the vast majority of proteins associated with the virus are not viral proteins at all. They're actually host proteins. In other words, the virus is a microcosm of the cell that made it. If it came out of a T cell, it looks like a T cell. If it came out of a macrophage, it looks like a macrophage. Okay. So, having discovered that the virus does this, we looked at mechanisms, and we made what turned out to be a fairly significant observation. The membranes of cells, or the shell of the cells, is comprised of 2 layers of lipids that keep the cell contained, right? We call it the lipid bilayer. And there are proteins floating throughout this surface that do all kinds of things. They take up nutrients for us, they get rid of waste from the cells, they have a whole variety of functions. Investigators at Yale and some other places taught us that the membranes of cells are organized. The lipids are organized, the proteins are organized. And one of those organizations or components is called a lipid raft. These are parts of the membrane with lots and lots of cholesterol and other single lipids. And because of the hydrogen bonding, there's a kind of bonding called hydrogen bonding, between the cholesterol and other proteins, these parts of the membrane are inflexible or rigid, and the rest of the membrane is more fluid. So the cell biologists, being clever, call them rafts. They're like little boats floating around in the water. And it turns out that one protein called CD45 is highly abundant on T cells that make HIV, but it's not present on HIV particles, right? And we were amazed that this was true because there's so much of this protein we could not believe that it wasn't on the virus particles. Well, Dr. Rose and his team at Yale determined that CD45 is not present in lipid rafts. So we just put 2 and 2 together. That if CD45 is not in lipid rafts, and CD45 is not in HIV, lipid rafts might be the point at which HIV leaves the cells, because it could leave that protein behind, if that makes sense. So we actually proved, more than 10 years ago, that lipid rafts are the site in cells where HIV emerges. It makes several important predictions. HIV will contain lots of cholesterol. HIV will have a certain protein profile. And there's some other things that it predicts, and all those things have been proven true. So we were the first to demonstrate that lipid rafts are the sites for virus budding. And it turns out, after we published our paper, there's been a whole slew of papers showing that not just HIV, but Ebola, measles, leukemia viruses, rotaviruses, they all do the same thing. So these lipid rafts appear to be really important platforms for lots and lots of viruses. Now, I'm a glorified nerd, right? Because in medical school, I still remember some of the lectures I had. I had my favorite seat, second from the left, on the left in the front row. I was always there, ready to take notes and ask questions. And I remember the lectures we had about cholesterol and how both important it is and how bad it can be when there's too much of it. We all know that high cholesterol is a bad thing, but it actually turns out that cholesterol is literally essential for life. We cannot be a living organism without cholesterol in our system for a lot of reasons. It determines the biology of membranes, it does all these things, but the bottom one is one I want to draw your attention to. When viruses infect cells, they often do so by a process called fusion, in which membranes become co-joined or mixed, so that the contents of the virus become continuous with the contents of the cell. That process is called fusion. And in many instances, cholesterol has been shown to be key for triggering the fusion reaction. So at the point of conception in humans, when an egg is fused to a sperm, for example, that cannot happen without cholesterol. So this lipid is literally essential for the process that starts life. So we wondered if cholesterol might also be very important for HIV, which brought me to another lecture that I had in medical school. And being the glorified nerd that I am, I can call it up in my head, and I remember these compounds called beta-cyclodextrins. Beta-cyclodextrins are cyclic circular polymers of glucose. Let's take glucose molecules and we join them head to foot to make a circle that looks like a barrel, shown there at the bottom. What's really cool about these barrels, the outside of the barrels love water, but the inside of the barrels like fatty things. They like lipophilic things. So if you take the middle form of cyclodextrins, beta-cyclodextrin, and add it to biological membranes, it will suck out the cholesterol from those membranes. So we wondered what would happen if we took this sugar and added it to HIV. And sure enough, if you take beta-cyclodextrin and add it to HIV, there's a dose-dependent, this slide shows you, the readout is a special assay we use to measure infection called luciferase activity. And along the right-hand side, you see the concentrations of cyclodextrin. That's millimolar, that's a concentration measurement. That at 20 millimolar, or 3% by weight, beta-cyclodextrin will completely kill HIV. Mind you, this is a sugar derived from starch. Very inexpensive to make. It's been used by drug companies for at least 3 decades. Everyone in the room has consumed it. I swear. It's in juices, it's in lotions, toothpaste, mouthwash. It's even on those towels you throw in your dryer to keep your clothes soft. That's how widely used this stuff is. So I'm telling you that to let you know that it's an extremely safe substance. But the point is that this simple sugar derived from starch will totally inactivate HIV. So what we proved here, and this is summarizing a lot of work by some talented postdoctoral students, cholesterol in the HIV membrane is absolutely essential for the virus. If you take it away, HIV becomes non-infectious. Not only that, the cholesterol in the cell membrane is also equally important. If you take that away, HIV cannot be infected. But what's really important for our purposes is that there's a third important observation, that if you take HIV-infected cells and you modulate their cholesterol content, even a little bit, they will start to make non-infectious particles, because the particles coming out lack sufficient cholesterol. So we've got 3 different mechanisms whereby we can manipulate cholesterol and control HIV. But this slide shows you what actually happens to the virus when we take away the cholesterol. This is called an electron micrograph, where we've amplified the picture of a virus 100,000-fold. HIV is so small you can never see it, even with an ordinary microscope. But with this special microscope, we can blow up 100,000-fold. The one on the left is a virus that has not been treated. The one on the right is one that's been exposed to beta-cyclodextrin. You can see that the one on the right looks a little funny, right? In addition to having an afro, you see the afro, it has a hole in the bottom of it. You see that big hole in the bottom? But it turns out that the viruses themselves have lipid raft-like structures, and when you remove the cholesterol, you destabilize the lipid raft of the virus, and it comes apart, and the internal contents of the virus leak out. Wow. So this virus is irreversibly inactivated. All we did was add a little bit of sugar to it. So the beta-cyclodextrin has depleted cholesterol, permeabilized the virus, and killed it. So what we're doing now is we're developing beta-cyclodextrin as a vaginal microbicide. We've taken the sugar, we put it into a gel. The gel is placed in the vagina, and if there's virus in seminal fluid, the virus comes into contact with the beta-cyclodextrin, loses cholesterol, and the woman would be protected. So far, we've done this in 2 animal models. We've done it in monkeys. We've also done it in a special breed of mice that have human T cells, called skid mice. And in both cases, the compound protected the animals extremely well. So what we're doing, we've also done acceptance studies in Zambia. We took the cream to Zambia. We gave it to women and men, hacked them, touch it, feel it, taste it, smell it. And in both cases, both the men and the women, they liked it, so we found that it was acceptable to them. They said they would use it if it became available. That was very positive for us. So we filed an IND with the FDA to try to get permission now to do the actual human studies needed to move this into people to use it. So just 2 months ago, we also got a big grant from NIH to test BCD as a therapeutic, not as a preventative. We're going to give it to people already infected and try to demonstrate that the virus can kill the virus in the body and be used as a therapeutic agent. And we're going to be doing that at Davis and Atlanta with our colleagues at Morehouse. So I'm very excited about this. This is something I wanted to do for a really long time.
Dr. Hildreth.
Yes, sir.
Like your very last point of testing it to see what it does in vivo, right? So, do you have animal models that you're going to use?
We do.
Okay.
We do.
You've shown that.
So one of the things we're doing in parallel to the human study is we're going to do the same thing in infected monkeys. I'm only doing it because I really want to do it. There's some things you can do in monkeys you can't do in humans. But we certainly got the grant based on doing a human study. And the safety profile of this compound is such that we don't think there's going to be any issues. There's a disease called Niemann-Pick type C disease where cholesterol accumulates in late endosomes and lysosomes. It's fatal. Typically, people don't live past 18. And around the world, there are about 60 children between the ages of 8 and 14 who are getting infusions of cyclodextrin twice a week at doses that would make pharmacologists cringe, something like 3 grams per kilogram. And some of them have been getting this for almost 2.5 years with no adverse effects, none whatsoever.
When you infect a primate with human HIV, do they get HIV?
Well, we have to use something called simian immunodeficiency virus. It's HIV's closest cousin. We can also do something that's kind of clever. We take the glycoprotein of HIV and we put it onto the SIV backbone to make a virus that looks like HIV, but it's actually SIV. And that's what most of the vaccine studies are done with. So, this last exciting story that I want to tell you, and I'll be quick about it, is an idea that I had that got me actually a Pioneer Award, which is a really wonderful resource. It's like $2.5 million over 5 years, and I essentially get to do what I want to do. Don't tell them this. But I got this huge grant based on this idea I'm going to share with you, which I think I'm becoming increasingly convinced that we're right. And it's something that we call natural pseudotyping and the potential role it might have in transmission of HIV. So the context of this is those 4 countries I've shown you before, Zimbabwe, Botswana, Swaziland, and Lesotho, at least through 2005, this is still really true, they have devastating rates of infection by HIV. And in fact, at this point, in some of those countries, the prevalence was north of 20%. That is, more than 1 person in 5 was HIV positive. And if you went to some of the villages in these countries, you'd either see very young people or very old people. It seemed like everyone in between was gone. Okay? And that's because of the people getting infected. But anyway, this is a devastating thing to see. But more importantly than that, there's an extraordinarily high prevalence of HIV in young women in these places that defies many attempts to explain it. It cannot be explained by sexual practices. It cannot be explained by the number of sex partners. It cannot be explained by use or non-use of condoms. Many types of studies have been done to try to get a handle on this. We happen to believe that there's a biological basis for this, and that's the same as the biological basis for super spreaders. The folks at the VRC, the Vaccine Research Center at NIH, estimate, and others do as well, that the likelihood of transmission of HIV when there's a discordant interaction, in other words, sex between an infected person and a non-infected person, is somewhere between 1 in 1,000 and 1 in 200. Okay? That might seem low to you, but when you think about the number of sex acts that happen, you know, it's probably not that low. But these super spreaders, it seems, that they have a much higher rate of transmission than that. Maybe 1 in 2 or 1 in 5 sexual encounters, they'll transmit the virus. Are they able to do that compared to everybody else? Well, we think the answer might be, at least in part, a phenomenon that we call natural pseudotyping. So, before I tell you this, I need to introduce you to a virus that we were using, which had an unfortunate story around it, called human gamma retroviruses. You may have read about this in the newspaper, XMRV. which was thought to be the cause of chronic fatigue syndrome, and also associated with prostate cancer. To make a long story short, we were asked by the NIH to study the virus for cholesterol. We started these studies, and I had this idea while we were studying this virus, and that's why I'm using it as a model, but it's just a model, right? So, let me just get right to the story. The tropism of viruses, this is really important, is determined by the glycoproteins and its receptor. Tropism means which cell type does the virus infect. For example, the tropism of HIV is for CD4 positive T cells because CD4 is the receptor, right? And influenza, for example, can infect a much broader range of cells because the receptor for influenza happens to be a sugar that's found on many, many cell types. But the point is that viruses infect cells based on tropism, which is determined by the attachment protein. All right? This is sort of virology 101. The attachment protein determines the cell type that can be infected. So HIV infects CD4 positive T cells, HGRV infects epithelial cells, because that's where the receptors are. Now in the laboratory, I can have one of my students take the CD4 molecule and the chemokine receptor and put it on the epithelial cells. The epithelial cells now become happily infected by HIV because it's now tropic for those cells because the receptors are there. Likewise, in the laboratory, we can take HIV, delete the envelope gene of HIV, the GP120 protein, and replace it with the attachment protein of another virus. So we've changed the tropism of HIV by giving it some other virus's glycoprotein. So now instead of just infecting T cells, we've created a virus that can infect whatever cell type the other virus can infect.
Super virus.
Yeah. And in the laboratory, this has been done for decades, that process is called pseudotyping. We give the virus a different type, make it a pseudotype, by giving it somebody else's attachment protein.
You tricked
Yes, we're playing a genetic trick. We're genetically changing the tropism of the virus by giving it somebody else's attachment protein. Well, we would like to suggest that this can happen naturally. That if two viruses infect the same cells and are replicating in the same cell, that virus A can take the attachment of protein to virus B, and virus B can take the attachment protein to virus A. In other words, that process I described to you that happens by us doing genetic manipulations can happen naturally when two viruses are replicating in the same cell. So we call it natural pseudotyping. And it simply depends on two viruses replicating in the same cell. So in this case, I'm showing you what would happen if HIV on the right, and HGRV on the left infected the same cell. We now have the possibility, shown on the upper right-hand side of the slide, that HIV has stolen the glycoprotein of the other virus. And now instead of having just the red attachment proteins, it's got the red and the green. It's been naturally pseudotyped. What does this mean? This now means that HIV can still infect CD4 positive T cells, because it has GP120, but now it can also infect epithelial cells because it has the attachment protein of a virus that normally infects that cell.
Is that good?
Yeah.
Is that good? It's good for the virus, but it may not be good for those of us. So are you with me?
Yeah.
Now we've now created a virus that has expanded tropism. It's not limited to CD4. It can now infect epithelial cells. Why should we care? Well, now, with all due respect to any of my OBGYN colleagues who might be in the room, this is my cartoon of a vagina. You know, it's a box. You can actually see that lining the wall of the vagina are the squamous epithelial cells, and at the bottom are the cuboidal cells of the cervix. But those cells in the vagina have lots of properties that make them resistant to HIV. First of all, they're cornified, which means the cells at the top are dead, and the living cells are found at lower levels. But they have these really amazing junctions between them, called tight junctions, that literally keep anything bigger than a small molecule out. That includes bacteria, that includes viruses. It's what we call a mechanical barrier. Not only that, the pH in the vagina is low, it's 4, which means that between the tight junction, the mechanical barrier, and the pH, HIV at the bottom there does not infect very efficiently because there's no opportunity. But imagine what would happen if the situation was the one shown at the top. That now, HIV has an attachment protein that is trophic for the epithelial cells. So now the very cells that should be keeping the virus out will welcome the virus in because they're now hosts for the virus. So this would change everything. No more mechanical barrier. Hello, welcome, come on in. Because HIV has stolen the glycoprotein from another virus. Are you?
Yeah.
Come on in. All right.
We want to see where you're going.
Okay. I wouldn't be telling you all this if I didn't have some data to share with you.
Okay.
So what we did was, we took a cell line that's able to support replication by both viruses, and it's called CM174, it's a T cell line. We infected those cells with either XMRV alone, HGRV, HIV alone, or with both viruses. That's what's shown across the top. We then took the progeny viruses, the product of those infected cells, and asked if HIV can infect primary cells from the vagina. These are primary cells actually taken from a vaginal biopsy of a normal woman. These are not cell lines, these are not, artifactual cells, these are the real deal. So we're measuring HIV infection by looking for viral proteins from HIV. So an infected cell will light up green, uninfected cells will remain dark. You can see for yourself that when XMRV is used, we don't find HIV because XMRV is not HIV. That's expected to be negative. If it's HIV by itself, shown in the middle, no infection because these cells do not have HIV receptors. But look at what happens when HIV is co-produced with XMRV. HIV has stolen the glycoprotein from XMRV, and now the vaginal cells get infected perfectly fine. I have lots and lots of data I can show you. When the virus is co-produced with XMRV, epithelial cells will support replication just like T cells will, because HIV has stolen the glycoprotein from XMRV. This is just another example. I have example after example, okay, showing that when HIV is co-produced with XMRV, that the virus will infect epithelial cells, which normally should not be resistant. And just to confirm that we're actually seeing what we're seeing, we can take an antibody, that is a protein that can bind other proteins, that is specific for the glycoprotein of XMRV, and ask if it blocks HIV infection in those situations. If my hypothesis is correct, the antibody to XMRV should neutralize HIV when it's co-produced with XMRV. And I wouldn't be showing you this unless the answer was yes. On the far left-hand side, you can actually see that in the presence of the polyclonal antibody to XMRV, HIV infection is blocked. We have other data to confirm that in this situation, natural pseudotyping is happening, and that HIV can steal someone else's glycoprotein. So what's the big deal? This has major implications, and I think this is why the NIH gave it its grant, because it has major implications. It may explain the high transmission rate among super spreaders. And there's a long list of viruses that are candidates. HTLV1, human T-cell leukemia virus, herpes, CMV. There's a long list of viruses that HIV could be stealing from to make this happen. And it happens to turn out that the epidemiology map of these other viruses overlaps with HIV in Africa, which is a little bit intriguing. The other thing is that there are lots of tissues in the body that become infected that don't apparently have receptors for HIV. Is it possible that this is happening by pseudotyping? For example, the genital tract of infected males. As far as I know, no one's actually demonstrated how the virus gets into that protective compartment in the first place. Maybe something to think about. But most importantly is, if you make a vaccine against HIV based on GP120, but HIV is using herpes simplex attachment protein to infect, your vaccine is really not going to prevent those initial infection steps. It might help to control the virus, but it's not going to prevent infection because HIV is using someone else's attachment protein. Likewise, if you're developing a microbicide based on GP120, it may be ineffective because HIV again is using someone else's attachment protein. So we're very excited about this, and we think that natural serotyping may at least in part be an explanation for why the infection rates are out of control in certain places. Now, because I was asked to do so, let me just tell you a couple of sad stories and one very happy story. Microbicides, which I work on, have had a major setback in the last 2 years. There was a very exciting study done. It was called, I forget the name of it, but they took a gel that contained tenofovir. Tenofovir is one of the most widely used HIV drugs. They put that drug into a gel, gave it to women. The women used the gel. As you can see, I'm sorry, the one that's grayed out, it reduced the risk of infection by 39%. And in women who were very compliant, it reduced the rate of infection, risk of infection by 50%. This was the first study to really demonstrate that microbicides could actually work. Unfortunately, in a later study called VOICE, where they expanded the study to include a much larger group of women, they stopped the study early because there was absolutely no evidence whatsoever of any efficacy whatsoever. And so the investigators involved in this study have been trying hard to explain what happened. Because the first study was beautifully done, well controlled, the data looked really solid. When they tried to expand it and do it in a much larger group of women, for whatever reason, there was absolutely no efficacy whatsoever. And there are lots of possible reasons for this, but that gave the microbicide field a little bit of a setback. Let's see. I want to tell you about two studies that are much more hopeful. One is the IPREC study. This is a study in which they gave men, almost 2,500 men in 6 countries, the one-a-day pill called Truvada as a prophylactic strategy. So these are men who are at risk of infection. They took the pill once a day. They followed them for, I think, 2 years, and they screened them to see who converted to be HIV positive. And what they found in this study was that among those men who were 90% compliant, the risk of infection was reduced by 73%. This was really one of the most exciting developments in a really long time. That by taking this once-a-day pill, they're not infected, but if they're at risk of infection, the risk was reduced by 73%, which is really one of the most positive developments we have seen.
Well, then what did they do? Tell them to go out and have sex with women who age 35?
No. They didn't ask them to change their behavior or their sexual practices. They simply asked them to take this pill once a day. But because of certain factors and practices, they were at risk for becoming infected. And among the men who again took the pill 90% of the time, their risk of infection was reduced by 3/4, by 73%. But, yes, sir.
Isn't the pill supposed to be also go with condom use as well still?
Yes, that's what I'm saying. They were encouraged to do everything that was supposed to be done, condom use,
Okay.
avoid risky behavior, but they also asked them to take the pill once a day. And Steve might have some additional thoughts about this study.
I was going to say exactly that. The study was done by actually increasing their possibility they wouldn't get HIV infected. So they got counseling once a month, they got testing HIV once for HIV, they got treatment for all of the diseases that might make their immune system more at risk. And still those that were able to take the pill all the time were the ones that were protected. Able and willing. I mean,
so the last thing I'm going to share with you is a study called HPTN 52. And again, Steve can make sure I get this right, but this is a very important, I'm sorry. We have the expert here in the room. But I did want to make sure you were aware of this, because this is a very important development that's caused a lot of excitement. And basically there are 1,753 reported couples. That is, one person infected, one person not. They had to fit a certain inclusion criteria. They had to have a pretty high CD4 count, between 350 and 550. They were randomly assigned to be in various treatment groups. But the bottom line in this study is, the most important thing is, they treated everyone who tested positive in this study. Right? Whether, because there used to be algorithms for when you put people on treatment, you know, CD4, viral, and all that. But from my perspective, what's really important about this is that all of the people who tested positive were put on treatment. And they asked these two questions. Would antiretroviral treatment of HIV positive individuals reduce transmission rates in a negative partner? And could you slow down disease progression by treating infected individuals? And the bottom line is that the study was extremely well done, and the data were very, very positive. And the thing I want to draw your attention to is the number in the middle, that infection rates and transmission rates were reduced by 96%. And overall, the disease progression was reduced by 40%. If any one of my two colleagues want to add something to that? Is that all right? Did I get it right?
What was the ethnic breakdown of the people in the study? All black Africans.
Well, there was some Indian, I guess, but
Some
yeah, no U.S. And almost all
Yes, sir.
And you know, we've been hearing this, but how it rolls out down the street is, first you got, your physician is not going to just write you a prescription for Truvada just for you to be protected from having HIV, and neither is your insurance company going to go ahead and release that prescription to the pharmacy, and how is that going to happen? Then you have Medicare. All of the theories of Truvada is great, but when it rolls out down to the street, it's not really feasible to happen.
Well, there's a
You
lot.
got your pharmaceutical company, and you got your physician. Physician writes the prescription. The pharmaceutical company is going to want to know why, and if the reason why is what Truvada is prescribed for, you got the pharmaceutical company that makes the decision with this $4,000 for 30-day drugs. So how do we make that happen? The bridge between the physician and pharmaceutical company and actually having it as a preventive measure.
Yeah, I think this is very typical of any new scientific discovery. We now have to figure out how it works in the real world and what are the ways we remove barriers to access for people. Some of the things you talked about are barriers, but there actually are lots of programs emerging to check and see what are the right ways to roll it out to make sure people can access it. Do we get the same results? Do we continue to get the same result in the real world now that we have the medical proof? And there's some insurance companies that are covering it. There's some doctors that are prescribing it. But the question is make sure people understand which, this was one drug, not every HIV drug. You can't just go to your cousin's medicine cabinet and start taking his drugs, and you need to take it every day. And so we are the company itself just got approval, and there are a number of demonstration projects, including one here in the Bay Area, to figure out what are the right ways to roll this out. We could have an all-day seminar just on this bill.
Yes.
So I'm not going to belabor that any longer.
And this issue of microbicides is really important because it's hard sometimes for people to take a pill every day. If you can incorporate a gel into sexual practice, that may be a really effective way of preventing infection. So the bottom line is we need, when I said we need a vaccine, I work on pills and I work on gels and I work on all of those things, and I do really want a vaccine, but a vaccine isn't going to do it all. We need all of those things, including behavior, including pills and all the rest of it. So there are some programs right now that offer the pills without any charge. But again, what you brought up is really important. It's about the long term and how's it going to be on the street. And I do think one of the most important things is our recent election, because we're not going to get health care for anybody if the election is on the other way.
Yeah, and I wouldn't want it, and I certainly want it to take away from personal responsibility.
Right.
For us on the street, that just gives the leeway to, I don't have to have any personal responsibility for anything. I can just do what I want to do when I want to do it. Appeal.
All right, I'm going to take off my official hat here. And I'm sorry if I've hurt anybody in ministries, but most people that are having sex are having a good time.
And they would much rather get to the place where they can get an injection when they're a little kid, not have to worry about HIV when they turn 14 or 18 or decide to start having children or having sex for any other reason. So I think all of these are just tools to help us control HIV, and we have to figure out what are the right ways to use these tools if we're going to actually end HIV. And no matter what, all of these interventions in the various places where people don't have resources, from my point of view, the reason I work on vaccines is someday if we had a vaccine that was effective, just like I don't have to worry about polio, people wouldn't have to worry about HIV. Not likely to happen in my generation. But microbicides, pills, all of it are ways for us to move forward.
So, my brother right here.
So I'm so honored to be in this room today and glad that that you're here. So I would like to have this opportunity to really invite you, since SMAC is getting its new site, probably we're working on that. We should have our new site on December 1st. We would like to really invite you to come back with the people of PrEP to talk with young black gay men about PrEP, because we're having this upstairs conversation and it is young black gay men that really need to be talking about PrEP. I don't really want to have a conversation about personal responsibility because Bishop is in the house, and I don't want her to really hear me say it like this.
Say what you got to say about
that. But kids are fucking every day. I mean, in real ways. And they're not talking about personal responsibility. They getting down. And so I really want to know what we're going to do, because we're having conversation in Alameda County, whether it's the Latinos or the black boys or who getting HIV. I don't care who getting it. I want black young men to start getting HIV in Alameda County. And we don't have services here for them. That many services, let me say it like that, so because I'm not politically correct all the time. We don't have that many services here for them. We don't have prevention services here for them. We don't have this for them. I just want them to stop getting HIV here. And everybody won't get funding for them, but they don't want to really serve these bad kids in Alameda County. So what do we have to do to get somebody to talk about PrEP for them here in Alameda County?
We'll work on that with you privately, but
no, you know what? That's why we're having the private. I thought this was the conversation for us, because.
So let me finish my thought.
Okay, thank you.
My thought is one of the most important things that's going to help is if we have the faith leaders in our community understand what the work is that we're doing here. They can help some of those young men realize that their lives still matter. And once they realize their lives matter, then they can make adjustments to what they do around how and when they're having sex. And whether it's taking a pill or biomedical intervention or making a decision that this next person is not the right person I'm going to have sex with, we have to have that conversation as a wider community. I will get on a plane and come and talk to them and share what I know. I will make that commitment. I can't make it for December 1st.
Okay.
Because I'm already committed to 3 places to speak that day. But I will tell you, I'll come back and help with that. And we'll make that part of our faith initiative here, part of our outreach here.
So I think it's time we're past the allotted time. I just want to end by saying that I've been in church since I was 3 days old, and I really understand how important black faith leaders are to this effort. And one of the things I think is still a big problem from my perspective, both as a believer and a scientist and a black male, is stigma.
Yeah.
And I always like to end by reminding all of us that HIV is a virus, it's not sin. AIDS is a disease, it's not sin. And so it's really okay to embrace this issue no matter what you believe in or who you believe in. And I think that's why it's so important to me to be part of Ed's effort, and that's why I was doing this in Nashville. I just want to thank you for your efforts and just let you know that it's so very important. And with that, thank you so much.